In the last video, we finished setting up the simulation and we are ready to start getting some results. Before running the simulation, you need to make sure that it is saved and set up for running. vSim will automatically set up your simulation when it is saved. Currently, in the bottom left-hand corner, we can see that it says Simulation Setup Changed. Save the setup for simulation changes to take effect. If we hit Control S, the simulation will be saved and it will be set up for you automatically. After being set up, in the bottom left corner it will say Completed. Click Run to continue. If there are no setup errors, then we can navigate to the Run tab. Here we have a few more parameters that we need to set before running the simulation. The time step of the simulation is crucial. It needs to be short enough that the fields do not propagate a distance longer than one cell before the fields are updated, but it shouldn't be so short that the simulation takes ages to run. A reasonable value for the time step was calculated as a parameter and called dt. We can set that to the time step property under basic settings, so that value will be loaded by default. Back under the setup and under parameters, we can see that parameter dt here. If we navigate to basic settings and time step, we can assign the parameter dt. Once again, we can save and set up the simulation to see our changes. Back in the Run tab, we can see that the default value for the time step has been updated. We can click Reset to set up values to load this value into the time step. We also need to choose an appropriate value for the number of steps. In this case, because we are interested in a far-field calculation, we need to allow enough time for the fields to travel the full length of the simulation domain several times. This is calculated as the parameter time steps, which again can be found by navigating to Setup, Parameters, and finding Time Steps. In this case, the result of the calculation is near 3,000, so that's the value we'll use. The dump periodicity is simply the number of time steps between each record of all the field and particle information that gets stored. A good rule of thumb is to try to get around 10 dumps for a good representation of your simulation results. In this case, that would mean a periodicity of 300. This is also where you can specify how many cores you want your simulation to run on. In this case, we will use 4. We can now click Run and watch for any errors. Depending on your simulation and available resources, this can finish very quickly or might take several hours. If the simulation ran successfully, you should see an output that looks something like this. At the end, there should be a print statement saying Engine completed successfully. Now we can navigate to the Visualize tab and start looking at our simulation results. First, let's take a look at the electric fields generated in the simulation. To do that, we can expand Scalar Data, E, and select E Magnitude. On the right here, this is the entire simulation domain filled with values of the electric field. We can clip this plot to see what's going on inside of the simulation with this box here. Looking at the plane controls, we can clip the X direction specifically. To see where the hand is in reference to all this, we can come down to Geometries and check this first box here. Now we can see the hand embedded inside of the electric field data. We can select which dump we want to look at for the electric field. As we pan through these, we can see the field changing slightly for each step. To change the color scale to see what's going on a little more clearly, we can come down here to the color table and set the maximum to something a little more reasonable. Now we can clearly see how our signal is penetrating the hand and interacting with the area around it. There are several other fields that we can look at as well, including the magnetic field, the displacement, etc. And in the next video, we're going to look at how we can analyze the electric field and check out the far field radiation patterns that it generates.